everybody. My name is Professor Jennifer Hill and I run Divide and Conquer Math, which is a YouTube channel and website designed to help you learn math on your terms. So this is the third video on limits in my Study with a Math Professor series. So this video is for difficult limit problems. If you've never seen one of these before, the way that these work is these are literally just there to give you extra practice to help you prepare for an exam. So my deep philosophy is it's not like you can just watch a video and be magically prepared to, take an exam. You've really got to get in there and practice. If you want to hear an entire breakdown of my philosophy of how you should study for exams, I highly recommend that you take a look in the description. I've got a link to how to study for exams there. So in this series, it's all designed for practice, laying a foundation, and this set of problems are really going to be kind of the trickiest to really keep you on your toes. So modify this problem set to your needs. If you are not one of my students and you see some problems in there that you haven't covered in your class, of course, then don't worry about them. And you'll want to get a hold of the problem set. So the problem set can be found in the description below. It's totally free. It's got everything that you need. It's got a list of problems, it's got the answers, and then for any problem, if you don't know how to do it and you want to see a lesson on how to do that, I've got links to all sorts of videos where you can watch extra examples of how to do them. So like I said, this video is not specifically lessons, but in this video I can direct you to the right lessons if you get stuck. And then the answer key is there, so if you get anything wrong, you can look in the description of this video and you will find time markers for each problem so you can watch a specific solution if you didn't know how to do it. So I'm going to start like I do all of these videos, where you will see me studying for about an hour. I'm actually going to be working kind of on my own stuff over here, and after about an hour I will let you know that we're done. That's just there in case you have trouble getting started. Maybe just having like a video alongside of you to motivate you might help, and you've got that problem set so you know what you kind of want to work on. So I highly recommend that you try to study this for at least an hour. I think that those problems might actually take more than an hour, so don't feel bad if you're not done. You can always start the video over or pause it or do whatever you need to do. And yeah, let's get started, guys. Hey guys, if you're not done, I'm going to start going through the problems, so either hit pause or you can start studying again. So starting with A, I've got the limit as x approaches 0 on the left of sine of x over the absolute value of sine of x. So you have to know something about how absolute value works with one-sided limits. So this is kind of like the more negative side of this particular limit. So that's going to allow me to rewrite this without the absolute value, which is the goal. So I've got now, if this is approaching on the left, that means that I can just rewrite this without the absolute value, and so instead put a negative here because I know how absolute value works, and this is approaching kind of that negative side of it. So let me just finish this. So this is then going to cancel out those signs. This is just going to equal -1. So if you're looking for more instruction on that, you're going to want to look up one-sided limits with absolute value, which I have some videos on, and I have linked those in the description or on the problem sheet. Okay, so B is very much a similar thing to A. So we have the limit as x approaches 3 on the left of this whole thing. And so notice, like, we're going to get this 0 in the denominator, but I can rewrite this knowing that, once again, I'm going to be on kind of the more negative side of this absolute value. So using the same trick that I used for the last one, the idea behind this is to rewrite this. Let's see, x minus 3, and then negative x minus 3. Okay, so I've got all this set up so I can cancel out these x minus 3's. And so now I'm just left with the limit as x approaches 3 on the left of this square root of x, jumping the gun here, square root of x over -1. And now I can just plug 3 in. So this will ultimately equal negative square root of 3. And so that's it. So if you are looking for more problems like that, you're going to want to look up one-sided limits with absolute value. Okay, so moving on to C here. So I have a sense of what I might want to do with this problem, but where I should really start is I should just like take a second to see what happens if I were to plug 0 in. So if I were to plug 0 into this, I definitely get 0 on top, and I would definitely get 0 on bottom. So I can see I get 0 over 0. So probably the best course of action, since this is like a fraction, would be to break this up and see what we can do. You could break it up. I guess alternatively, the other thing that you could do is you could also factor the x out. So there's more than one way to kind of approach this. And now that I'm thinking about this, I actually think I want to factor the x out. So we'll go that direction. But if you did not go that direction and you get the same answer, that's okay. So if I factor the x out, so let's see, I get cosine x minus 1, so there's what's on top. And then I've got 3 sine of x cosine of x. So now that I see this x here and a sign down here, I feel like I'm going to probably have to use this little theorem here, which we know that this equals 1. So that's what I kind of want to invoke here. Okay. So let's break this limit up into bite-sized little chunks here. So I want to put the x and the sine of the x together, and then I'll have the cosine of x minus 1 over 3 cosine of x. Okay, so there's this limit just rewritten so that I can kind of use this little fact. So this part here, this is going to go to 1. And then for this part of the limit, so cosine of x minus 1, so cosine of 0 is 1. So this becomes 1 minus 1. So this becomes 1 minus 1. And then in the bottom, this becomes 3 times 1. So in the end, I have really just 1 times 0. So the whole thing ends up equaling 0. Now, if you're looking for more instruction or more practice with this, you really want to look up these types of problems. Again, I have links to them if you look in the description or on the problem sheet. Okay, so moving on to D here. So just notice what happens if I plug 0 in. I get 0 over 0. And then also notice that I really can't simplify this any farther. So it's not like I can cancel the signs out. The 5 is not going to come out, right? So that's not how trig functions work. So we've got to leave this as is. And so when you kind of get stuck and you have the sine function, this once again is going to kind of beg for us to try to use this little fact here. And you can flip-flop this, so theta could be on top and the sine of theta could be in the bottom. But this is basically what I would like to use. So I need to make some manipulations to this so that I can do that. So notice there are no like just freestanding x's in this, but that's really what would make this problem a lot better. So what I'm going to do is I'm going to multiply the top and the bottom both by x, because what that's going to allow me to do then is to break this up and get me a little bit closer to using that theorem. So I take this x down here and I place it with this sign, so there's one part. And then I've still got the other part of this fraction, so I've got this x over sine of 5x. Now, this part of the problem is good to go. This part is going to require a little bit more manipulation, because we know that these two things have to be the exact same. This says 5x, so I need a 5x here. So to finish this off, then what I'm going to do is I'm going to multiply this by 5 over 5. So now, let's see, I'll have the limit as x approaches theta of sine of x over x. So I'll take that top 5 and put it with the x. And then this other remaining 5 here, I'll just put it at the end of my limit, just so we can better visualize it. Okay, so now we are ready to go with this. So this is going to 1, this is going to 1, and this of course is just going to 1/5. So the value of this limit is just 1 over 5. And once again, if you're looking for more practice with these types of problems or more explanation, or you want it broken down more, you just need to look up limits that involve this particular property. Okay, so moving on to E here. So what you'll notice is that we've got cotangent here, so it would probably be in our best interest just to rewrite this so that we can visualize, you know, all the parts of this limit. So let's see, I'll have sine of 3x, and then this is what? Cosine of x over sine of x. So there's kind of the whole thing reimagined. And this is important to see, because what we end up with is, once again, the indeterminate form, 0 over 0. Notice that you cannot simplify this. So sine of 3x and sine of x, those are two different things, so we just have to kind of leave those alone. So once again, we want this little property here. Okay, so in looking at this, I'm going to use the same trick I did for the last one. So at the moment, I don't have any freestanding x's, but if I had those, then I'd be really ready to go. So I'm going to go ahead and multiply. Let's see, I'll just multiply them over here. So I'm going to multiply this whole thing by x over x and start to manipulate this. Okay, so I'm going to have the limit as x approaches 0. So let's see, I'll take x over sine of x. So I took this sine of x and paired it with this x. Then I will take sine of 3x over x, and then I've still got this cosine of x. So here's kind of my limit rearranged. And I can use my theorem here, but I need to manipulate this because this is 3x and this is just x, and these need to be the exact same. So I will do the same thing again, where I will multiply this thing by 3 over 3. So now if I rearrange this whole thing one more time, I get the limit as x approaches 0. I've got x of sine over x, and then I've got sine of 3x over 3x, and then this other 3 here, I'm just going to dump it in with the cosine of x, so 3 cosine of x. Okay, so now we can invoke this. So this is going to go to 1. This is also going to go to 1. This is going to go to 3. And cosine of 0 is just going to go to 1. So what I'm left with here is 1 times 3 times 1. So this just equals 3. And so once again, you can look at problems that have to do with this. I have whole videos where I break this down and explain all of this if you want a refresher of kind of the strategies for that. Okay, so moving on to F here. So the first thing that you want to notice is that this is a limit as x approaches infinity. So that kind of changes probably the approach that we want to take. And the other thing to notice is this is kind of like a like a pseudo rational expression. So you've got all these exponents here. And so that's really what's going to drive everything. So where is your largest exponent? Your largest exponent is right here at the 4/3. And so since that is in the denominator, that's really just going to cancel out everything else. So this whole thing is just going to end up going to 0. But if we want to just see all the detail just to kind of prove that, what we can do is we can divide everything by x to the 4/3. So I'm going to divide all of this by x to the 4/3, and then I'm going to divide all of this by x to the 4/3. So let's just set that up. Okay, so I went ahead and I set up just the calculation. So I just wanted to show you kind of everything if you really wanted to work out this whole calculation. So the thing to note here is that, so all of these, everything on top, all of these pieces are going to go to 0. These are all going to go to 0, so maybe I'll note that. All of this is going to 0. This is all going to 0. So you really just have then 0 over 1 as x goes to infinity, so the whole thing will just equal 0. And so if you're just looking for more problems to practice that are like this, so again, you can look, and I've got just links to other videos, but these are kind of just limits as x approaches infinity. That's what you're looking for. Okay, so moving on to g here. So now we've got the limit as x approaches infinity of this square root over this. So this is really still just like two rational, or this is really just a rational expression in disguise. So the thing that you want to think about, and I've explained this in way more detail in kind of other videos, but just to kind of jog your memory. So you want to think about what is happening with this dynamic of taking the square root of the highest power here. So yes, I know that we have x squared minus 2, but like this square root of x squared, kind of what impact does that have? That kind of turns this into just x, right? If this was all that we had. So we're kind of thinking about how this plays along with the whole problem. And this is going, and understanding how that square root impacts things, that dictates what we're going to divide by. So I can actually divide everything then just by the power of x, just by a singular power of x. So let me just show you kind of how this all goes together. Okay, so the thing is, when we get to the square root, you have to make a modification to this so that you can divide this into the square root, because as it is, this is just x, it can't be divided into the square root. So what I have to instead turn this into is not x anymore, but the square root of x squared. And now you can kind of see why it matters that we understood kind of how the square root and the x squared kind of played with one another. So let me just show you kind of what is happening in the background. What is the math here? Okay, so I've set this up, and so now that I have rewritten x as the square root of x squared, this allows me to actually set up a calculation here so I can finish simplifying. And so now that I have all of this set up, I can think about what happens as x goes to infinity. So this part here is going to 0, as is this part. So what I am left with then is the square root of 1 over 1, which is just 1 over 1, which just equals 1. So that's it. And so once again, if you're just looking for more practice problems like that, you're really looking for limits as x approaches infinity, kind of difficult limits involving that. Alrighty, so let's now take the limit as x approaches 0 on the right of 1 over x to the 1/3 plus 1 over x minus 1 to the 5/3. So you'll notice now, you always want to kind of start by just plugging in the number just to kind of get a sense of what's happening here. And so this fraction is going to be 1 over 0, so that's a problem. This fraction will not, so this is not really the problem. What we have to worry about is this one. And it is a limit law that we are allowed to technically break this up into two separate pieces. So I can break up this limit, and then I can break up this limit as shown. Okay, so there we go. So now I've got these two different limits. Like I said, this one I can really just plug in the number and evaluate this. So this is just going to end up giving me 1 over negative 1 to the 5/3, which if you work that out, that's just 1 over negative 1. So this piece here is just equal to negative 1, so I've really just got to worry about this. And now I've talked about in a lot of videos how to kind of approach this. So you can't simplify this any farther, right? We can't use like an algebraic trick here. It's already simplified. So basically it's probably going to equal either positive or negative infinity. And so how you want to determine that is kind of up to you, if you want to use a table or if you want to just kind of look at it and analyze it. So I can just kind of quickly create a table just to prove my point. So here's my table, and then let me just choose a couple of points on the right side of 0. So notice the 3 points that I've chosen, so they're getting progressively closer and closer to 0 on the right side. And so then if I were to evaluate those, I can tell now from my y values that I've plugged in here. So this is getting progressively larger. So it's getting larger at a very slow rate, but these are getting progressively larger. So the smaller this number gets, i.e. the closer we get to 0, this is just going to get bigger and bigger. So what that tells me then is the value of this is really just going then to positive infinity, which means that my answer, I've got infinity, and then I've got this plus, this would be negative 1. So this really drowns everything out. This doesn't really matter. The infinity is drowning out the -1 part. So the answer here then is that this just equals positive infinity. So if you are looking for other things to practice, you can look up infinite limits, and of course I've got links to that in the description below. Okay, so moving on to I here. So this one's a little bit tricky, and I do have a lot of example videos on this. So if you feel like you need more instruction on this, be sure to check those out. So the thing to notice with this is, you know, we can't plug in infinity, like not technically, but in the back of our mind, we can kind of think through it, right? And maybe I'll write this in this orange color just to kind of indicate. So I've got this infinity, this square root of infinity minus this square root of infinity. Like that's what's really kind of happening here. And it's hard to really say then what this is going to end up. But it looks like, I mean, you can't really do calculations with infinity. So maybe you might say like in your gut, oh, it's going to be 0. But since we can't technically do calculations with infinity, this is not good enough. So now we've got to get a little bit more finesse with this. And so since I can't simplify this any farther, instead what I'm going to do is I'm going to use the conjugate. So I'm going to multiply this by the conjugate. So let's see, this will be the square root of x plus 4 plus the square root of x plus 1. So I just multiply the whole thing by the conjugate like this. Okay, and so now I can kind of work through and multiply all this together. So let me do that. Okay, so I've worked this out a little bit, and I'm going to simplify this a little bit more, so let me keep going. Okay, and so now I have something that I can work with. So this calculation as it is, I can't do, like I said, it would be wrong. It's not mathematically solid to do this calculation. But this actually kind of relates to one of the most basic properties of limits, which is if you have the limit as x approaches infinity, this 1 over x, this just equals 0. So that is something that we've seen, we've proven, we know that, and that's really what's kind of going on here. And so now we also have resolved the issue of, you know, before I had like this infinity minus this infinity thing. So it was a little unclear as to what was actually happening here. But now I've got, if you think about what's happening with the denominator, this part is going to infinity, this part is going to infinity, and you're adding them together. So obviously the whole denominator is going to infinity. So the denominator of this fraction now is going to infinity. So because of that, the whole thing ends up going to 0. So our intuition was correct, but it wasn't mathematically sound. And so to make it mathematically sound, now we were able to get it to match our intuition. So it's nice when that happens. And so if you are looking to practice more problems like that, you can look for limits at infinity or as x approaches infinity using the conjugate. You can look that up and you can find some more problems that are similar to this. Okay, so J is very similar to the problem we were just talking about, the last one. And this has another similar trick with it, I guess. So if you just take a moment to think about what's actually happening here. So it would be wrong to write down calculations with infinity. That's not mathematically sound. But in our mind, we can think through that. And that's usually how most people think of things. So if I think about this, if I think about what was happening with this, if I could do this, just what would be the behavior with this? Well, okay, if I really whittle down just the key terms of this square root, and I think about what's happening with this square root of negative infinity squared, this would end up kind of like, it feels like we've got something like another infinity minus infinity type situation, right? So this feels very similar to the last problem. It just kind of presented itself in a weird way. However, as I said before, you can't do calculations like this. So if you were to write this on a lot of tests, I think a lot of teachers probably wouldn't take this. I mean, I guess it depends on the teacher, but I know that I was not allowed to write things like this when I was a student, and I also don't allow my students to do that, so that's why I give that advice. But of course, everybody's different, so maybe somebody out there will allow you to do it. So I want to show you a mathematically sound way to kind of show the answer to this, because we probably have some intuition as to what this equals, but we need a mathematically sound way to prove that. So once again, I'm going to multiply this by the conjugate, like this. And, okay, so now let's just multiply this all out. Okay, so I've gone through and written out kind of all the detail here, and I simplified this line to the next. And so this, very similar to the last problem we were just talking about. So I can't do calculations technically with infinity, but I can always leverage the fact that the limit as x approaches infinity of 1 over x equals 0. And that's basically what this is in disguise, right? We have a couple of x's down here. Now, there are a few issues that we should probably think through before we finish this. So you might be thinking, well, now we've got this square root of x minus this x. Don't we have like an infinity minus infinity type problem? And we don't in this case, because this limit is going to negative infinity. So if I really wanted to think about what happens then, so as I go towards negative infinity, so in this part, whatever number we're talking about as we're approaching infinity, this ends up being positive, and then the negative of a negative ends up becoming positive. So really, we end up kind of adding two positive things together, so the denominator gets larger and larger. So if that doesn't make sense, let me know in the comments, and I can always upload another explanation. But that's kind of what's happening here. It's really the sign play. So because this is going to negative infinity, this minus x, we can really think of it more as a plus x, because we know which direction this is heading. This is going to end up being something negative. So all of that is to say that this does indeed equal 0. So if you're looking to practice this more, you can just look up limits at infinity using the conjugate. Okay, so moving on to the limit as x approaches pi over 2 of secant x. So the easiest way to really approach this one is if you know what the graph looks like, then this is like instantaneous. But I want to approach this from, what do you do if you forgot what the graph looks like? Because I think if you know what the graph looks like, this is very obvious. But it's not obvious if you don't know what the graph looks like. So, all right, first of all, I notice when a lot of students approach a problem like this, they like to rewrite it not as secant, but 1 over cosine of x. And I think this is good if you are a little shaky about what these look like, because then you can use the unit circle. But the thing about the unit circle is you just have to be careful of how you apply it. So, all right, let me pull up a unit circle. Okay, so I've got my unit circle, and I think having this visual, if you get really stuck on something, it's always very helpful just to think through. So here's pi over 2. And if you think about it, so cosine stands for the x coordinate, right? So at pi over 2, what we see is that on the left versus on the right, the cosine function is going to go from positive to negative, right? So that really matters now in this context, because this means that on the left and on the right, these are approaching two different values. And by the way, you should really have the unit circle memorized for a calculus exam, it's incredibly handy. And if trig functions are something that trip you up a lot, having the unit circle can just be a very handy reference for when you get a little stuck. So, okay, so what I'm saying then is we've really got to compare two limits here. The limit as x approaches pi over 2 on the right of this, and then the limit as x approaches pi over 2 on the left of cosine of x, because we know that the left and the right are actually approaching kind of, they have two different behaviors. This side is positive, this side is negative. And now more importantly, we know that the cosine of pi over 2 is 0. So we've got this fraction that's 1 over 0. And since we can't simplify this anymore, this is really going to be an infinite limit. So what that means then is now we have to think about what is really the behavior on each side of this. And the behavior of pi over 2 on the right side, so it's going to get really more and more positive because we've got 1 over this little value, right? So if you look at the unit circle, so pi over 3 to pi over 2, so this x value is getting smaller and smaller, and it's less than 1. So if I take 1 over that x value, it's actually going to become a larger and larger number. 1 over a decimal ends up becoming a very large number. So I can tell then just from the behavior of this that this side is going to end up going to infinity, while on the other side, so this just becomes, this stays negative, right? So we're going to have that same behavior, but it's going to be 1 over a negative decimal. So this ends up becoming a very large negative number. So on the left side, this will approach negative infinity. That's a terrible looking infinity. Let me make it again. Okay, and so now from this analysis, I can see that on the left and on the right, I approach two different values. So this, the value of this limit, we either say it diverges because it goes to two different limits, or in some classes you say it does not exist. So whatever your class does. So this limit, you know, it doesn't have a value because it's approaching two different things on the left and on the right. So if you're hoping to get more practice with that, you can look up limits or infinite limits, and you can find other things like that, maybe infinite limits with trig functions. All right, so for this next limit, I have the limit as x approaches infinity of cosine of x plus 1, all of that over x. Okay, so this one now we've really got like an infinity over infinity situation. I cannot make infinities today for some reason. So we can tell that we're going to have to do some other analysis here because this is an indeterminate form. So let's think about splitting this into two pieces because we know that that's a thing that we can do with limits. So I'm going to break this up into cosine of x over x, and then the limit as x approaches infinity of 1 over x. Now this limit here is simple. This is like a property of limits. This is like the most basic infinite limit. So this one I already know goes to 0. So really I've just got to figure out what is happening with this guy here. And you might be thinking, what can we possibly do to this to figure it out? Because we can't simplify it, right? Cosine of x over x, that's as simplified as it gets. And you could try, I guess, with a table, but the problem is that can feel a little tricky with the unit circle. So a stronger way to approach limits at infinity with trig functions are to use actually the sandwich theorem. So that's the sandwich or squeeze theorem, and I have whole other videos on that, so you can check those out. And so what I want to do here is set up an inequality that I know the cosine of x kind of falls in between. And I want to keep my values just positive for right now. So I'm going to take, I know that the absolute value of the cosine of x is between 0 and 1, right? So I can sandwich it there. And then if I divide all of these parts by x, and this is just going to positive infinity anyways, so that's kind of a good thing. But if I think about what's happening with these, So as x goes to infinity, this will go to 0. This will obviously go to 0. Therefore, this will also go to 0. So the overall value of this limit will just be 0. So you can always look up problems having to do with the sandwich or squeeze theorem and infinite limits or limits at infinity. That's a way you can kind of practice these. Okay, so moving on to m here. So now I've got the limit as x approaches infinity of the natural log of 1 plus 1 over x. So really the only part of this limit that has an x in it is right here. So we just have to worry about what happens as x approaches 0. Or sorry, as 1 over x approaches infinity. This whole guy here is just going to end up going to 0. So the value of this then ends up becoming, we can just drop the limit because we're going to take it. So the value of this is really just this, right? So the natural log of 1 plus 0, which is just the natural log of 1, and that just equals 0. Now, for this particular limit, there are two things I kind of recommend that you review if you thought that was tricky. I recommend that you take a look at limits at infinity, but also if you just didn't remember this fact, just review your properties of logarithms. I have a really quick video where I go through all those properties, so if you really struggle with that, you feel like you forgot all that stuff, don't worry, that's totally normal, and so you can check out that video. Okay, so moving on to n here, so I have the limit as x approaches 2 on the right of the natural log of x minus 2. So you can do this in a couple different ways. You can make a table for this, or another way that I've kind of talked about is to just think about what is kind of the behavior of what's happening here. So you might have to know a little bit about the graph of the natural log. So if you know the graph of the natural log, so if we take a second to think about this, so let's see. Let's just quickly sketch something. So this is just the graph of the natural log of x, but this will help us answer our question. So the closer your natural log function gets to 0, really your function ends up going to negative infinity. So that's really the answer here. So in this particular function, the closer we get to 2, the closer this is going to get to 0. So this whole value is going to go to negative infinity. Now, if you did not know that, if you forgot the graph or whatever, and you're like, oh, I wouldn't know that, then the alternative would be for you to make a table and just have some values of 2 on the right. And then you could also figure this out that way. So for that, you can just look up videos on infinite limits. I have a bunch of those, and you can make the table if you need to refresh that. Okay, so moving on to question 2 here. So determine the values of a and b so that f of x equals, so I've got this whole piecewise function here, and I want to determine for what values is this continuous at every x. Okay, so let's set this up. Here's that piecewise function, and the idea here is that piecewise functions don't always connect, and we want to figure out how to make this connect end to end. Now, if you have no idea what this problem is talking about, you know, if your class doesn't cover it, of course, you can just skip over it. But in my class, so we've looked at problems that are like this. So I have other videos on this, but I wanted to just do one as a refresher. So in this case, I have 3 pieces. And so with 3 pieces, so if you just think about having, here's 1, 2, 3 pieces, and this is just a random piecewise function here. But if you just think about, if I want to make these connect, how many connections would I need? Well, I need a connection here. So here's one connection, and here's the second connection. So this is kind of what I want to force in this situation here. Okay, so to do that then, I'll start with these 2 pieces here. So I want to take 4 and I want to set it equal to ax plus b. Now, I know that these 2 things will be equal at what point? At this point where there's this changeover, right? So where we go at x equals -2, we switch from this function to this function. So to make this slightly stronger, what I want to do is I want to plug in that -2. Okay, so I can't go any farther with this right now, so I'm just going to leave this alone. And now I'm going to pivot to this other part of the function. So I'm going to have this ax plus b now equals -2. But where would this happen? Where would these be equal? Again, it's at that point where they're changing, so here at 4. So I'm also going to plug 4 into this. Okay, so now I have 2 equations here. So notice what I have. I have this equation and I have this equation. So this is actually now a system of equations, so I can set all of this up. So if I rewrite this, I have negative 2a plus b equals 4, and I have 4a plus b equals negative 2. Hooray! Okay, so now I just have to use whatever methods I want to solve this. I'll use the elimination method. So what I'll do is I'll go ahead and rewrite the second line as all the negatives like this. And so now I can just combine. So I get negative 6a equals 6. So my a equals negative 1. And then I have to solve for b. So let's see, I think I've got just enough space to do that. So let's say that I plug in negative 2 times negative 1 plus b equals 4. So I'm plugging this negative 1 into this equation right here. So this becomes 2 plus b equals 4, therefore b will equal 2. So now I've found my two values of b where this is true, at a equals negative 1 and b equals negative 2. Now, one thing I want to just point out here is make sure you double check what a question like this is asking. Sometimes they just ask for the values of a and b, and other times they'll actually ask you to determine the function where this would be true, in which case you would have to restate this answer with your a and b plugged in. So that's just like a little thing, but you know, depending on the class that you're in, you know, that could ding you. Okay. So moving on to 3 here, explain why x to the third minus 10x plus 2 equals 0 will have at least 3 solutions in the interval from negative 5 to 5. So this problem is really screaming for the intermediate value theorem. And so I guess the reason I threw this into this problem set is one of the things I find that is the most difficult for students on calculus tests is when theories get asked up, because a lot of times students just won't even review anything like that. So make sure that if you have no idea what this is, like look through your notes and see if this was covered, and look for any other theorems that you might have covered, because when you get into calculus, it's pretty common to ask about theorems. So this is partially why I threw this in here. Okay, so I have the graph here actually, so that is going to make this much easier. So the intermediate value theorem says really two things. So this is the actual, well, okay, I said theorem, but it's property. So when a function has the intermediate value property is when a function has all the values in between 2 points a and b. So if you have a continuous function, so in this case I have this is continuous, right? X cubed minus 10x plus 2, this polynomial, we know this is continuous. So what I know is that all of the values between negative 5 and 5, it doesn't matter what value of x I choose, they're all going to be there. Okay, that's one thing that the intermediate value property or theorem says. But one consequence of this that matters for this particular problem is about root finding. So this is one of the second consequences of this property. So a root is a solution to this. So that's exactly what we've got, right? Is we've got something equal to 0. And if a function goes from negative to positive or vice versa, then it has to have a root. Okay, so this is now like using that along with the graph and kind of all the other information that we have, we're really good to go here. So notice if we look at this graph, so I'm going from negative 5 to 5. So a little more specifically, I can see that like at this point here, so notice what's happening. My values go from negative to positive. So I know that there has to be a root there. And then from here to here, I go from positive to negative, so there has to be a root here. And then finally, from here to here, somewhere in here, there's got to be this root here. This question is not asking what are the roots, it's just asking how do you know that they exist. And so it's really a consequence of the intermediate value. Let me write this as property, not theorem. And so that's really your solution, is to just explain that you know that this function goes from positive to negative kind of in these little intervals. You can see it in the graph. And this function is continuous. So by the intermediate value property, we know that there have to be at least 3 solutions. There's 1, 2, 3. So that is the kind of answer that you would want to give. Okay, so moving on to the next part of this problem set. So I have 4 questions here asking about asymptotes, and I think it's very important to highlight how to do this from a calculus perspective. One thing I notice when I give tests is when I have questions on asymptotes, students tend to revert back to what they know from pre-calculus, and they don't give me a calculus level answer. So while the answers might be simple, I want to just show you what I'm really looking for with these type of questions. When we talk about a horizontal asymptote, so we're really talking about a limit here. This is the definition of a horizontal asymptote, and here is the definition of a vertical asymptote. And I've broken these down in great detail in some other videos. So I just wanted to kind of remind you though that at the end of the day, from a calculus perspective, asymptotes have to do with limits. So if you're asked in a calculus class how to find an asymptote, then you need to relate that back to limits. So here, I might know that I have an asymptote when the denominator equals 0. So I can tell just from looking at this that I will have an asymptote at x equals -2. So this is great if you know this, but this is not usually good enough for a calculus class. You will usually be asked to back this up with theory. So now if I think about this, so I have a vertical asymptote at x equals that point if I can take the limit as x approaches that point and show that it equals positive or negative infinity. So from a calculus perspective, I just need to use one of these limit definitions to really prove this, that this is the asymptote. And I'm not going to show you all of the work to prove this because I've shown quite a bit of infinite limits. So I'll drop a link to how to do that in the description if you're not sure. You can make a table here or whatever you want. But this will ultimately equal positive infinity. And so that fulfills this definition. And so because that equals infinity, that means there is a vertical asymptote. I'll just write VA at x equals -2. So this is how you use calculus to show there's an asymptote. And then to show the other asymptote, so a horizontal asymptote, that requires me to take the limit as x approaches infinity of this, and this is just going to end up equaling 0. And so then according to this definition, when this equals a number, that means that there is a horizontal asymptote at y equals that number. So then I can say there is a, I'll say HA, horizontal asymptote at y equals 0. So that's how you use calculus to make your point. You don't want to use old class material to make your point. You want to make sure you're really applying the definitions and theorems. So for B here, so this is very similar to what I was just talking about with A. So for problems like these, you need to use really the definition of an asymptote. So these are the limit definitions as part of your answer. So I've got these definitions here. Okay, so in this case, if I just try to think of what would the asymptotes be, most students can just look right at this and say, oh, there's going to be an asymptote at x equals -2. But remember, you do have to back this up with calculus, so I have to actually use the vertical asymptote definition to prove this. So to do that, then what I want to do is take the limit as x approaches -2 on the right, and then I've got x squared plus 3x minus 1 over x plus 2. And so then I can tell just by looking at this, so this is going to give me something negative on top. So if you think about what's going to happen with this and you know the behavior of plugging in something negative here, the top will end up being something negative, the bottom will end up being something positive, so this will end up going to negative infinity. Now, if you didn't follow that at all, no worries. So then the alternative, of course, if you're not sure what the value of this limit's going to be, you can make a table. So we've got these values here. These are on the right of -2, and if I evaluate this, you can see in my table, so here are my values, so I'm getting more and more negative. So the value then of this particular limit is equal to negative infinity. And because this equals negative infinity, then by the definition of the vertical asymptote, I know that there is a vertical asymptote, I'll use VA, at x equals -2. Okay, so there's one. So let me make some space. And now to just find a horizontal asymptote, so I need to take the limit as x approaches infinity. So this is the limit as x approaches infinity of x squared plus 3x minus 1 over x plus 2. So I can see now with this particular problem that the dominating term is in the numerator. So if you're not sure what I mean by that, I would highly recommend that you go back and watch just some of the lessons on limits and infinity. So this whole thing is going to end up going to actually positive infinity. So that does not fulfill our horizontal asymptote definition, but actually there is a oblique asymptote here. So to figure that out, what we're going to want to do is we're going to want to use polynomial long division. So let's set that up to find the oblique asymptote. Okay, so I'm dividing everything by x plus 2, and then I've got x squared plus 3x minus 1. So if you totally forgot how this works, I have a whole video where I actually just talk about how to find oblique asymptotes. So be sure to check that out. So, okay, so what I have to ask here is how many times, or what do I have to multiply x by to get to x squared? So that would be x. Then I multiply x by x plus 2. So this becomes x squared plus 2x. And I subtract all that off. So if I subtract off that result, I'm left with x minus 1. And then what do I multiply x by to get to x? That would just be plus 1. Now if I subtract that off, minus the x plus 2, so you'll notice in this case that I get -3. Now when you find an oblique asymptote, you don't care about the remainder, you just care about this first part here. So this is actually where our oblique asymptote would be. So you have to do a little bit more work if you actually have to find the oblique asymptote. But that technically does not have one of those calculus definitions, yet we still have an asymptote that we have to know to look for. So for C here, so you're going to have to use, just like you do with the other two problems, you have to use the definitions of horizontal and vertical asymptotes to help answer this question. So you want to use calculus to back up your answer. So in looking at this, so are there any values that would make a 0 in the denominator? So yes, if we had 0, then we would have a 0 in the denominator. So I can see that this will equal 0 when x equals 0, because this will give me 1 minus 1. So this is not a calculus level answer though, so to make this more calculus-y, I want to use this one. So I want to use the definition of the vertical asymptote. So I just have to incorporate a limit into my answer. So I'm going to have the limit as x approaches 0 of 2 plus e to the x over 1 minus e to the x. And let's see, I need to take a one-sided limit, so I'll just take it on the right. It doesn't really matter. Okay, so however you want to prove this is kind of up to you. I tend to make tables with these types of problems, so I'll set that up. So I've got my table, and I'm just on the right of 0, so my values here. And so if I evaluate this, so the closer I get to 0, I can see that this gets more and more negative. So this limit is going to go to negative infinity, which fulfills that definition of the vertical asymptote. So what this means then is there is a vertical asymptote, so I'll use VA at x equals 0. And you could also go on the other side of this if you want. I only do one side when I prove these. All right, so now let's talk about horizontal asymptote. So what would happen if I try to evaluate this with the limit as x goes to infinity? So let's see, this looks kind of crazy. And you might be thinking to yourself, oh, I don't know what happens because it looks like I'm going to have like an infinity over negative infinity. But remember, we're still looking for like a dominating term here. And the trick here is to usually divide by that term of highest degree, which in this case, I guess is like e to the x. So just what happens if I divide everything by e to the x? So let's just think through that for a second. So I divide all parts by e to the x. So e to the x divided by itself will just give me 1. I've got 1 over e to the x minus 1. So I've just divided all of this by e to the x to simplify to this. And now I have something that is much simpler to look at, because I know that as x goes to infinity, this will go to 0 and this will go to 0. So I am just left with 1 over negative 1. So this whole thing will just equal negative 1. All right, so in this case, this is one horizontal asymptote. So I'll put horizontal asymptote at y equals negative 1. But in this particular case, we're not done. So we have to find another one. So let me make some space. And now I'm going to have the limit as x approaches negative infinity of this guy. All right, so I've set everything up. Now, this really matters in this case that this goes to negative infinity, because we can kind of think through what happens in this case. If x is going to negative infinity, this would really be the equivalent of this situation. So I could still have just x going to infinity, but rewrite this as e to the negative x. That gives me the same thing, right? But the thing about this is e to the negative x, so having that negative exponent there, this allows me to think about the problem a little bit different. So if I have the limit as x approaches infinity, I don't even have to divide anything to figure this particular one out. So I can just rewrite this as 1 over e to the x, and then this other one, 1 minus 1 over e to the x. So I just used the definition of a negative exponent to work this out. And now I can see this will end up going to 0 as x goes to infinity, as will this. So this whole value then will just be 2 over 1, so this just equals 2. So, oops, I'm sorry, I dropped those negatives here. Should be a negative here and here. So what this means then is I have a second horizontal asymptote at y equals 2. So I've noted both of those here. So that one's a little tricky. Sorry, my dog is barking. So for D, very much like all the other problems in this section, so you have to use these definitions to really bring calculus into this particular problem. So just looking at this, you might know just by looking at this that the denominator will equal 0 when x equals negative 2. And that's great, but we just have to back that up now by using calculus. So to do that, I can just take the limit as x approaches negative 2. On the left or right, it doesn't really matter in this case. They'll both equal the same thing. So I can set that up, and then I can kind of go through all the work to figure this out. And I've shown tables for some of the other problems, so I'm just going to kind of fly through this one, I guess. So if you think about this, negative 2 on the right, so this ends up being a negative number. That means I have something negative on top that I'm cubing. So the result on top will be negative, while the result on bottom, so this ends up being just under 8. So anything that is on the right side of negative 2, if I cube it, that will be just a little bit under 8. So I have something negative on top and something positive on bottom. So what that tells me then is that this limit is going to approach negative infinity. Now, if you're not sure about where that came from, I highly recommend either looking at just some of the previous examples that I just did or checking out infinite limits. And so what this means then, according to the definition of a vertical asymptote, which I have listed here, this means that there is a vertical asymptote at x equals negative 2. And now for the horizontal asymptote, so now what I want to do is I want to take a look at what happens as x approaches plus or minus infinity. So in this case, as I go to infinity, all right, so if I evaluate this, if I divide everything by x to the third, which is my highest power in this case, this will leave me with 1 over 1 plus 8 over x to the third, which means that just this part here is going to end up going to 0. So this whole thing equals 1. So because this equals a number, that means that there is a horizontal asymptote at y equals 1. And you'll get the same value if you went to negative infinity, so I'm going to omit that. So for the last two problems, we're going to, so I've got that stated here, so this is problem number 5. So it says to take a look at the definition of the limit. So I have the precise definition of the limit here. So this is definitely a tough type of problem. Some classes make you memorize this, so if that's something that your class is going to make you memorize, just be cognitive of that. So I need to find the delta that works in this particular situation. And if you aren't sure what all of these things mean, I break these down. It takes actually a lot to kind of explain what all these things mean. So I highly recommend that you check out one of those videos. But for our purposes, I'm just going to kind of go through the typical motions for one of these exercises. So I'm kind of assuming that you've seen these before and you just need a little bit of a refresher of how to set these up. So the first thing I've got to do with this problem is figure out what is the value of the limit. So the way that these are set up, you're taking a look at the limit as x approaches c of f of x. So in this context, we're looking at the limit as x approaches 4 of the square root of 1 plus 2x. So that's going to come out to the square root of 1 plus 8, which is just the square root of 9, so this equals 3. So this is my L in this case. So where we start with these types of problems then is we start by examining f of x minus L, and we set that less than epsilon. So in this particular context then, I'm going to have the square root of 1 plus 2x minus 3 is less than 0.01. So what I want to do for this is I'm eventually trying to back this into my delta. So I'm really starting like with my y coordinates right now, and I need to solve this for x. And then my delta has to do with my distances around my x, so then I can bring that in at a later time. So to solve this, I separate this into the 3-part inequality like this. And then I can add 3 to all sides. So I get 2.99 is less than or equal to 1 plus 2x, which is less than 3.01. And then if I square all sides, I'll get 8.9401. And I will get on the other side 9.0601. So let me make some space. Okay, so continuing to kind of just solve for x, so I need to subtract 1 from all sides. So that's going to give me 7.9401. It's less than 2x, which is less than 8.0601. Divide all sides by 2, so I get 3.97005. And then that's going to be 4.03005. And so now I've kind of gone as far as I can. So I want to be within 0.01 of my y's, and I know that this is kind of like the area around my x's. These are very specific x coordinates, but I want to talk about a distance around my x coordinates. So I need to think back to what was my limit approaching in the first place. So I need to now bring in this x minus c is less than delta part of the definition, which if I bring in the context of this problem, that's going to be x minus 4 is less than delta. So we're ultimately going to solve for delta. So to do that, I need to set up the 3-part inequality. And I first start out by solving for x. So I've got this 4 minus delta and this delta plus 4. Okay, so there's kind of everything that I've got. So I've solved for x now in 2 cases as far as I could. I have this case here where I solved for x as far as I could. And now I have this case here. And the whole point of this is to actually find the delta. So I've got enough information between these 2 parts now to help me solve for x. Now if you feel really confused and you're not sure kind of what's going on here and you want a deeper explanation, again, I highly recommend that you go back to some of my other videos where I really break all of this down, kind of assuming that you remember the gist of this at this point and you're just kind of looking for a refresher. Okay, so let me make some space so that we can finish this. So these were kind of the two key pieces of information that we needed. So now I'm just going to kind of set them up end to end. So I've got this delta here corresponding to this side of the x coordinate, and then I've got this delta kind of corresponding to the other end of the threshold around the x, if you will. So I've got 4 minus delta. I'm going to set that equal to 3.97005. And then I can just subtract the 4 off to get negative delta equals negative 0.02995, which means that my delta equals 0.02995. And then in this other case, so I've got delta plus 4, this is going to equal 4.03005. So if I subtract off the 4, I will get that delta equals 0.03005. And so what you want to do with these types of problems is when you have a choice of deltas, so you're looking for what is that minimum distance that you need around x that will ensure that we are within 0.01 of our limit value. So in this case, I have two different distances. I have this one and I have this one. So what you do then is you just choose the minimum of the two. So this would be the delta that we wanted. Ooh, okay. So if you want to check out more about that, I have lots of other delta epsilon proofs where I do lots more examples like that. So if you're looking for more, don't worry, I've got you. And now for the very last problem. So prove the limit statement. So this is really kind of referring to finding the epsilons and deltas that we need to make this particular statement true. This problem differs from the previous one because in the previous one, I'll just bring it up here. So in the previous one, we had a specific epsilon. So we had this epsilon is equal to 0.01. And this problem here has no specific epsilon. So we're dealing with like the most general case of epsilon that we possibly can. Now the steps are the exact same as the last example, except we're just dealing with more theoretical values. So I'm still going to use that precise definition of the limit to get me through this. So to prove that this works, I have to just find the delta that would work for the epsilon in this particular case. So I have to start out by, let's see, oops, let me grab the other color. So just using this definition, so I have f of x minus L is less than epsilon. So I have no epsilon in this case, so I just plug in the relevant information that I do have. So in this case, this would be 5 minus x, that's my f of x, and my limit in this case is 4. So I still want to solve this for x. So we're trying to find the delta that would correspond with the epsilon. So to do this, if I simplify, this is going to become negative x plus 1 is less than epsilon. So to solve this for x, I set this up as negative epsilon is less than x plus 1, which is less than epsilon. And so then I can subtract 1 from all sides to get, let's see if I have enough space over here. Negative 1 minus epsilon is less than negative x, which is less than epsilon minus 1. And just be careful when you divide all sides by negative 1 here, because your inequality signs, these need to flip their direction since you're dividing by a negative. So now I have, this becomes 1 plus epsilon is greater than x, which is greater than 1 minus epsilon. And I just want to rewrite this because I hate when my inequalities go in this direction. It's just a personal preference. So I'm going to rewrite this as 1 minus epsilon is less than x is less than 1 plus epsilon. Now, this little fact here, I've noticed that students who even know how to do this, they'll forget this part here and then it throws the rest of the problem off. So just watch out for that. Okay, so I have my kind of x value that I'm floating around here. So now I need to bring my delta back into this. So let me clear some space. And now let's think about our delta. So in the definition, I've got that x minus c has to be less than delta. So we want that delta to ultimately be in terms of epsilon, and we need to write this in terms of our particular problem. So my c in this case is equal to 1. So I'm going to rewrite this as x minus 1 has to be less than delta. And I'm going to go through all the steps to solve for x again. So this becomes negative delta is less than x minus 1, which is less than delta. I can add the 1 to all sides. Let's see, add the 1 to all sides. So I get 1 minus delta is less than x, and this is going to be less than delta plus 1. Okay, so now I'm in the same situation I had last time. I have this had to do with kind of working with the functional values, and then this is thinking about what I want to do with my x values. So just like I did last time, what I'm going to do here is I'm going to take those two pieces and I'm going to set them up end to end. So I'm going to take this end and relate it to this end, and then I'm going to take this end and I'm going to relate it to this end. So I've got 1 minus epsilon equals 1 minus delta. You're solving for the delta in this case, so people get a little bit thrown off as to what they're actually solving for. So if I go through and solve this, so I get negative epsilon equals negative delta, which means that delta equals epsilon. Okay, now let's do the other one. So I've got 1 plus epsilon equals delta plus 1. So if I subtract the 1 from all sides, I get epsilon equals delta. So you'll notice in this case, the delta that I want, they are the exact same values, right? So what this means is for this particular limit, if there's a certain distance, if there's a certain distance that I want to be around that limit, around that y value of the limit, then I just have to be the same distance around the x value. So that's what this is getting at. It's going to be the same value on each side, and you will get to that limit value that you're looking to, or within that limit value. So in this case, my answer would be, so this is kind of everything that goes into proving it. And so this would be the delta that we're looking for that kind of rounds the rest of this off, I guess. Now, as far as how you actually present that, that can be a little bit different for everybody. I think that everything I've shown here really does kind of prove this. You might have to adjust this to kind of your own instructor's expectations, but if you were in my class, kind of everything that you've shown here would prove that this limit does exist. Whew. All right, so I am like totally exhausted now. That was a lot of limit problems. I am super curious to know if you found this helpful. If you have watched the whole thing, consider hitting that subscribe button or liking this video or sharing it with your friends. And thanks guys, I'll catch you next time.